Our topic this afternoon is mold cooling design made easy. During this webinar, you will see quick creation of complex water circuits, speedy placement of cooling components using a rich set of catalogs, fast installation of many baffles of various depths, how to analyze the circuit for correct water path, and cooling analysis results. Our presenter today is Dan Branch. Dan is Support Manager for CimatronE. Dan has more than 17 years of tooling experience, and while working for CimatronE, he has been assisting mold makers identify and implement improved design and manufacturing processes, as well as providing customers with world-class technical support. As you listen to Dan's presentation, please feel free to ask questions by typing them in the questions pane on your computer. Dan will answer them at the end of the presentation. As a reminder, this webinar is being recorded, so you will be able to listen to it at a later time online. Thanks again for taking time today to be with us, and here's Dan.
Thanks, Christina. Before we get started, I'm going to take a minute to share a few fast facts about CimatronE. With more than 30 years in the business, CimatronE is a world leader in CAD/CAM solutions for the mold, tool, and die industry. CimatronE is used daily in over 35 countries on more than 40,000 installations. And not long ago, a study done by the independent research company, the Aberdeen Group, concluded that CimatronE customers deliver tools even faster than those that they deemed best in class. Well, in injection molds, the importance of an efficient cooling system cannot be overemphasized. The water flowing through the mold is the primary means of removing the heat from the plastic part, and as the part cannot be ejected until it's cooled, this has a direct impact on the bottom line. In a diagram of cycle time, the overall time spent cooling the part makes up the largest portion. So it's not unusual to find that a 1 or 2 second reduction in cooling time can lead to a 10 or 20% increase in production. But just rapidly cooling the part isn't the same as efficiently cooling it. Controlled, repetitive cooling around the entire part is also really vital to controlling the dimensional stability and the mechanical properties of the plastic part time after time. Meaning, a properly cooled part won't be as likely to warp or be stressed or brittle. The best way then to ensure a successful and profitable run of plastic parts is to make sure the mold has a well-designed cooling system. To the mold designer, cooling is just one of the working systems in the mold. The shape of shutoff, the size and arrangement of cavities and slides, this is always the first concern. Then typically the gating of the part must be addressed next. Designing the cooling system generally comes near the end of the mold design process, out of necessity really. So in order to achieve the efficient cooling that we know we must have, it's often necessary to work around obstacles like inserts and lifters and other moving parts. The mold designer has to be creative when it comes to cooling, but he has to be fast and accurate as well, as there isn't any time to waste. What can really help is a CAD system that knows mold making with specific cooling functions that allow for design freedom and ease of use. So let's take a look at a few examples of injection molds and see what the particular needs for cooling them are. For that, I'm going to switch over to the latest version of CimatronE CAD/CAM system. So the first example mold design is one for a smaller part. This saw handle is representative of many plastic parts that are for consumer use. It's not too long or too deep, and it can be molded in a standard off-the-shelf mold base. The mold design is in process. Besides the cavity and core development, this side of the tool has seen the addition of 6 core pins and a standard lifter assembly. That's for an undercut feature on the part. And in addition, the design of the ejection system has already started. As important to productivity as good cooling is, if the part can't be ejected, the mold just isn't going to work. So a few important ejector pins are already in place here. The first task in regards to cooling is to decide what components will receive water lines. Items like core pins and lifters are often too small to get any good cooling inside them, which is usually fine. If there is some concern about removing heat from small inserts, one thing the designer can do is to choose to build them from a material with a high rate of thermal conductivity. There's aluminum and many bronze alloys which have a much higher thermal transfer rate than tool steel. And that can be very useful for pulling the heat out of the plastic and toward the cooling circuit. So in a mold of this type, the core block is typically the only component in the B side of the tool, which is what we're looking at, that would receive cooling lines. The surrounding plates do get hot, of course. Actually, the overall temperature of the entire mold should cycle up and down in conjunction with the molding cycle. But for tools with individual cavities like here, adding cooling into the plates isn't really a big contributor towards the goal, which is removing the heat from the plastic part. In one cavity, the cooling design can be thought of as a circuit. It'll have an inlet and an outlet, and it'll trace a path through the block. The depth of the circuit from parting line is the first consideration. It should be near the part, of course, but not so near that we risk drilling holes into any of the mold features. So when the mold designer is thinking about what kind of circuit will work best, he needs a tool that shares the same thought process. Cimatron allows me to just start tracing out ideas with the familiar sketch tools. Right now I'm thinking about what side of the mold the water should enter and exit from, but mostly about creating a thorough path that gets around the part well. It is possible to make calculations involving the heat content of the plastic being introduced and the many factors involved in removing that heat. But most cooling circuits are designed using good rules of thumb and practical experience. So bending the circuit around contributes to turbulent water flow, which is a good thing for pulling the most heat from the steel. We only need to be careful not to make the circuit too long or too complex. It's generally agreed that the water should be kept moving and that the water exit temperature only be around 10 degrees hotter than what's coming in. And I'm going to add a few dimensions to some of these lines so that they're where we expect them to be. So from the cooling circuit sketch, Cimatron takes me to the cooling object function. And here's where I can concern myself with the actual drill size of the water lines and get a nice preview of the water layout. In most cases, dividing the water into parallel channels isn't really recommended. So next, what I'm going to do is add some plugs. But right now, my main focus is on just improving this circuit design. I can turn on a visual analysis. That will help. So what this will do is actually offset the water line diameter and give me a clear indication of where I might be in collision with a surrounding component or hole. At a 1/4 inch offset, I do start to come into contact with some of these previously placed ejector pins. And the actual intersection is shown as a red curve. So I can decide if that is safe enough, or maybe if my water line dimensions should be adjusted. It's always good to have options so the design can be accurate to the actual block on the shop floor. Everything about this circuit can be controlled in this function, from the size of each channel to the type of the drilled end to the overlap distance. So I'm going to approve this water layout, and that's going to instantly translate into drilled holes in the block. My next order of business is to get the plugs and the other water components in place. Now, these are all going to be purchased standard parts. So what I ideally want is to access 3D catalogs. These will save me time in design. Cimatron ships with catalogs from 29 different worldwide vendors that supply the mold and die business. So access to those catalogs is just through a simple dialog. It lets me browse to a particular vendor. Then I can narrow my choice down by category. Now usually then I would be expected to pick the component size. But Cimatron has found a way to attach some intelligent rules to many of these catalog parts. So I'm not even really required to concern myself with the pipe plug size. The software understands that the lines are for water and that 1/4 inch NPT plug is appropriate for these drilled lines that I have. So they will fall into place on any line that I choose to pick. Now those components are now added to the design tree, and as well a bill of materials that's being kept for this job. Another great time saver here is that when a catalog component gets added, it's also cutting in any pocket or thread that the component requires. Built-in holes like this really cut down on the repetitive tasks you have to do while designing. Come back for my other plug here. This is going to be placed in using the same method as the first. And again, the rules here allow me to just pick the water line that needs the plug, and I have the correct size. To finish this circuit, I should really add some quick connect extension plugs. These are the components that are going to reach through the surrounding plate and bring the water into and out of the core block. And that's a pretty good overview of the cooling by circuit mentality for an injection mold. Now, the larger the part, the more circuits and different levels that are going to come into play. So we'll leave this example behind and move on to another. When it comes to really large parts, or a typical automotive tool, where a left and right part are both required, a different type of strategy is often applied. Cimatron is a popular choice where mold design for automotive is being done because of its strength in complex surfacing and its ability to handle the tough jobs. So in this example, the core block is nearly 6 feet long, and designing a cooling system of long winding circuits isn't really an effective way to pull the heat out of so much plastic. The distances are too great, and the cooling effectiveness of the water is going to decline. So instead, molds of this type are usually designed with straight-through channels and interrupted by baffles that direct the water up near the part surfaces. I'll turn some of that on. What we'll see here is that each channel is a circuit unto itself, and it can be drilled to a depth that's very near the part from the side here. The baffles, then, they serve to direct the water up into the higher parts of the mold steel. And as you can see, there may be a lot of them. The general school of thought is that even a rise toward the part of 1.5 inches is worth placing a baffle to gain. And many shops that work on jobs like this have 5-axis gun drill capability now. So baffles or water lines at angles are usually not a problem, and they're used to get cooling lines in where they're really needed the most. Because of all the channels exiting the sides of the tool, a lot of external piping is used on molds like this. And these are all connect to water manifold assemblies bolted to the sides of the tool. So in this way, a large quantity of fresh water can be supplied, and all the heated water can be collected out. Now I want to show a second example to really illustrate the difficulty that cooling system design can present. This is another big job with all the moving parts and replaceable inserts that are so common to large automotive tools. The cooling design in this tool is so complex that it's really hard to fully appreciate it. Some of those lines are for delivering water up into the larger inserts in the tool. These often have their own circuits. So this is a good example to look at. Designing a water system of this magnitude takes a good deal of thought and expertise. The mold designer can afford some time to plan this out if it means a quality plastic part will be the result. But he can never afford to lose time creating the holes, placing the components, and getting the plate to the shop floor. And that's where the CAD system comes in, by providing functions that understand the task, but also work with the natural thought process of the mold designer. So on that topic, for illustration purposes, what I'm going to do is open a much simpler mold design where I can show how the functions work, but without so much distraction. So in this mold, let's see how we can design a cooling system by way of individual channels that's still in a quick and automated way. Rather than start with a sketch, this time I'm going to go right to my cooling component catalog. pick the component I want. And I can place this connector plug on the side of the plate as many times as I want, all in one operation. When I use this type of component add, what Cimatron is doing is expanding on the idea of cutting the hole for the plug to include the entire cooling channel. So let's look at what we have here. The green cylinder being shown is the water channel, but the larger cylinder represents the safety distance that I want around it. Now both of these values are editable on the fly, and they do remember your preferred value. So we'll change one of those just to see the preview change. But control over the channel depth is the real highlight here. Instead of a simple default, I can ask the system to automatically set the hole depth in a number of ways. So in this case, I'd first like to check and see if I have any potential collision problems. And I'll find out by setting the hole depth option to no interference. What that does is extends each channel until it encounters a violation of the safety envelope. And it's quickly apparent to me then that one of these lines is stopped well before the others. As that plug was placed a little too close to a core pin hole, what I'll have to do is adjust the dimension on it, or I haven't put any dimension, so in my case I'll just slide it over a little bit here. So right away that channel preview is already going to adapt to a new position. And I can see here that I'm assured I have my 1/4 inch safety distance around these water lines. That's nice to know. It's really the main thing I wanted to know. I'll just switch back to Delta for a simple entry in this case. Now we'll go back to that catalog one more time. And in the same way, I can create some connecting channels just by using a pipe plug. So the channel and the safety distance, they're shown using the same principle as before. I naturally want automation wherever I can get it. So here Cimatron is able to control the hole depth based on something else. It's based on whatever cross channel I'd like to choose. So for every plug that I'm placing, and that can be who knows how many, the depth can be controlled independently. So adding baffles is next. And the idea, of course, is to get the water funneled up near the part. In the past, this required a lot of time to measure and fit each baffle individually. But Cimatron has applied this same strategy of automating the hole depths into placing baffles as well. Let's take a look at that. I'll have to add a few references here that'll assure that the baffles are where I want them to be. which can be edges of the part or actual cooling lines that we've already drawn up. So once those are all positioned, they just now take a look at them here. Now the baffle blade might need to be adjusted, which it does here, to sit across the water channel. So once again, the depth is easily controlled. We have our offsets. And this time we'll ask the system to set the actual baffle length by how close I'm willing to get to the part surfaces. And that's the safest option, again, the no interference. So that not only checks the tip of the channel to the mold surfaces, but also the sides of the channel as well, using that safety envelope. So that all looks good, and we'll apply those with cut. And you can see how just doing this with the channel for each type of component can build quite an extensive circuit without too much trouble. Now, I mentioned previously that all the components being added to the design are being compiled on a bill of materials. So when you have jobs that contain potentially hundreds of baffles, any extra help for the shop is going to be much appreciated. So while we were at it, CimatronE added in a click here that will generate a chart for all the baffle lengths. This would be something that you could print off, and each of the numbered baffles can be prepared ahead of time out in the shop. And I can see here also that the baffle function is doing a nice job of choosing the right standard part, because on any baffle that has a length over the 6-inch standard, it's calling out the longer size, so I can order the right part. Well, as we all know, even though we designed with the best of intentions, it's possible to make a mistake on occasion. So with that in mind, CimatronE has provided an analysis routine for checking the completeness of a water circuit. It's called Mark Cooling Circuit. And any given water design is going to be made up of numerous connectors and components. So the first thing the system wants to do is identify those. And that's just a press of a button. The function really relies heavily on display by color. So after it's identified the components, I can toggle this display and see the results a little better. So here, 3 types of parts have been found. We've got our baffles, we've got ins and outs, and we've got dead ends. And now that the system understands that makeup, what I can do is pick a starting point and run an analysis. So that would be any of these lines. And once again, we'll use a little help from this display control. Simulating the water flow down this particular circuit finds no real problem. The blue color is what illustrates running water, and it finds an out that matches with my in. So the water design isn't really any too complex here. It hardly justifies even the need to be double-checked. But I wanted to show this tool. And actually, I can bring up a better example to show what potential problems this helps us to find. When we get back into the real world of difficult molds that are going to have complicated cooling, a verification function like that is actually a very welcome tool. This design isn't as big size-wise, but the massive cooling channels and baffles that are in these kinds of molds really make it difficult for anyone reviewing the job to see what is taking place and to find these individual circuits. So that's where we'll use our verification tool again. So if we were to pick just one example, like before, the system here, it first finds all the connector types involved. And in the analysis result, yellow is the color that's used to indicate a trouble spot. So here, the yellow channels are highlighting a path that has two possible routes to take. While something like this might be intentional, it's more likely that a line has been drilled too far, or that an extra plug was left over from some change. Either way, identifying this problem now allows the design to be corrected before the drilling gets done in the shop, and that's important. Another topic that I should really touch on today is what is known as conformal cooling. The mold industry is always looking for new ways to optimize cooling, especially in tall cores or moving slides. And traditionally, these are cases where baffles or bubblers up into the core are going to be used. But using those types of components is really just a compromise. It's based on ease of manufacture. In an ideal world, the cooling circuits would often mimic the part contours, and we wouldn't be limited to round channels. Any shape would be possible. Now, sometimes you can approximate a circuit like this by machining smaller inserts and laminating them together. But what has really made conformal cooling a topic of conversation lately are the new technologies for additive manufacturing. So what we generally now call 3D printing has been around for more than 20 years, and in that time the costs have come down and the tolerances have really gone up. Plus the spectrum of materials that can be used is greater. And a core in a mold like this can now be 3D printed and metal and function quite well in a harsh environment, that is plastic molding. So this may be a very good option. By their nature, conformal cooling channels are unique to every part. They're going to be designed based on the shape of it. But Cimatron does support this method of design, and we can run cooling analysis, like we just saw, on circuits like these as well. So earlier I mentioned that most cooling design is done by guideline and practical experience. It's not that formulas don't exist to estimate cooling needs. They do. But it's just that there are a huge number of factors and variables that come into play. So that's where modern molding analysis software can come in. It can do all of the complex calculations that are required to simulate thermal activity. And it can feed back sound advice based on plastic flow and temperatures. So to finish up our discussion on mold cooling, I'm going to show you the result of an analysis done using MoldX 3D, which is a world-class flow simulation product and a partner of Cimatron. Now the part we're going to look at is the saw handle, the one we did earlier. The runner design, the cooling design, the cavity size, these are all things that can be imported directly from the mold design in Cimatron and used in MoldX 3D. Of course, before a simulation can be ran, some molding conditions have to be set, and this is a dialog that helps me do that. The material is a very important choice, and there's a huge material database here. And then obviously all the things about the machine timing, computation choices. It's all in this area. So I've already done the run, and we can look at these results. The tree here holds a lot of information about the run. For example, in the material area, it shows this melt temperature that my ABS is going to be injected at. It also shows mold temperature range. It shows the ejection temperature that's safe for the material, and what temperature even it starts to freeze up at. These are all things that will help me decide how the cooling circuit is doing. Well, simulation of the plastic fill is the big reason that molding analysis is used, of course. On this part with the one tunnel gate, we can see the flow front progression happen over the fill time, which is the graph on the side there. If I want to pause the animation, I can see at any point a very accurate picture of the part during the fill. So this is one of the most helpful displays that it does, but there are many more. Knowing the flow pattern means having precise knowledge about where the weld lines are going to be in the part. And if a weld line is going to be a problem, then I would know to fix that, either by changing the gate location or the gate quantity, and then I'd run the simulation again. The flow also shows me where the air traps are going to be. And this, of course, in turn gives me good information about where to add vents in the mold. Lack of proper venting is really a major cause of many molding flaws, so this is very useful information. And there are all kinds of other results I can view in the filling analysis here. Some of them can also be plotted out. For example, I can look at the sprue pressure graph. Let's take a look at that. And run it and see the pressure move while it corresponds to the filling on the screen. Okay, let's take a look at the cooling results, as that's our topic for today. So with the given water layout that we designed, what we can see is that the part temperature, which is again is the graph on the side here, at the moment of ejection, the part temperature is generally fine. The bluer colors are under the 90 degrees that I would like to have to eject. If we look underneath, though, around the gate, the part is still showing a bit warmer than I would like. So right away, I have to consider at least getting some more cooling into this area of the core. Now, time and temperature naturally go together. So let's look at a graph of the cooling time. And what we're going to see is that the part itself is generally cooled rather quickly. But the time graph is out to 79 seconds, which is far longer than I would want for a part like this. So what would be helpful is to take a look at it with a different time scale and see where the trouble lies here. So I can do that using this display, and it lets me actually drag through the time. And what I'll see is that the part itself is generally fully cooled by around 15 seconds or so. It's the runner that is retaining the heat too long. it won't be fully cooled until more than a minute after the part ejects in this case. That might be okay, assuming that it ejects out of the mold without sticking, but at least now we know. Another way to see those hot spots is by viewing this result. This is the melting core result. So again, this is at the time we hope to eject the part, and any plastic that I'm seeing in this display is still above the freeze temperature for this polymer. And again, it's a bit more than I would hope, especially when I'm looking at the deep ribs that are in this part. At the skin of the part, we can also see there may be trouble. Now this time the scale is not by temperature, but it's by percentage of the frozen part wall. And the red in these ribs is a genuine concern to me. Getting another cooling channel in this area now becomes quite important. That is, unless I want to rerun this whole process and use a slower cycle that adds in more cooling time. So I've gotten a lot of good information from the time it's taken to do this analysis. Other things. Another thing I can see is what's cooling efficiency. These are the percentages of cooling that each channel is giving. The balance isn't bad here despite the red and blue colors. If we look at the graph, the cavity side is really only doing about 5% more of the cooling work than the core is. And really that extra line that I want to add into the core might make things about equal. So the balance of cooling between the core and the cavity is here. And that's also something that the warp analysis in MoldX 3D will look at to help figure out possible warpage in the part. Now, while we're looking at cooling channels themselves, we can check other things like pressure drop as the water travels from in to out. Or the Reynolds numbers. And these are a measure of the turbulence the water has while it flows through the circuit. So that's good to know. We discussed earlier that turbulent water is a good thing. And we can actually even look at the water temperature itself. So as the water comes in this simulation, it's at 60 degrees. And at the exit, it's being shown about 64 degrees, which isn't bad at all. In fact, it could be taking more heat out. So in the cooling simulation, I can adjust the water flow rate, maybe make it go a little slower. Or what I'd probably do is use this information and go back into Cimatron and adjust some more cooling channels into the design, see what else I can get. Well, at this point, I've really finished with all the topics I hope to cover today. The rewards of a well-done cooling system are great. It's really one of the most important aspects of injection mold design. But we all know there's a constant pressure to build molds faster, better than ever. So it's imperative to depend on smart CAD functionality. Rule-based design, automated channels, circuit analysis, all of these things help us do the job. And hopefully I've been able to show you some good examples of that today. But now I'd like to turn it back over to Christina for any questions that you might have.
Thank you, Dan, very much. I first want to remind everyone, before we get to the questions, if you have any questions, please feel free to ask them by typing them into the question pane on your computer, and we can go through them. Let's see. We did get a bunch of questions. First one, Dan, would there be any problem with using both methods of water creation by channel and by circuit in the same job?
No. There won't be. We looked at both examples of that and kind of divided it up into you know, a small mold and then a big mold, but they're both functionalities that are there in the product, and you can use whichever one works the best, or both. No problem.
What if I use a catalog part that is different from what Cimatron provides? Can I just use one from the manufacturer?
Yes, although the catalogs, as you saw, have some rules based into them. So in order for all that to work, that's something that you will have to do a little work on the part for and prep it for Cimatron. Like I mentioned, we do have a lot of catalogs, but some of our users do change them a little bit if they need something specific. So again, not a problem, and well-built catalog parts are the biggest help in getting some of this to work the way you want it to.
Somebody else has, what other aspects of mold simulation can Moldex 3D do?
Well, I'm much more a Cimatron expert than a Moldex 3D expert. However, there was a packing simulation that was run there that we didn't look at, and there was also, I mentioned the warping, which is another full set of analysis that it's doing for you, and you can look at all those results together, which really helps make the intelligent decisions that you need to make. So it does quite a bit.
We have one about, does the core or cavity block need to be a closed object for these waterline features to work?
Okay, so I know what's being asked there. A lot of that is based, obviously, on cutting solids. The answer is no, though. This is a good question for Cimatron, because Cimatron is never really dependent on fully closed models for this type of activity. It would only be a problem if the water lines were crossing through, let's say, a boundary between a couple of these solids. So a little stitching, yes. Fully closed, no.
We have another one. Is there a way of calculating the 10 existing temperatures as a way of adjusting your water lines?
You know, I think what's being asked there, I mentioned at one point about the water temperature and the rise in temperature that's generally allowed or thought to be useful. And by the way, that's just out of my textbooks here and from experience I've seen. The water is absorbing the heat into carrying it out. So it probably has an efficient limit. 10 degrees is just a number, but it's generally thought to be a good number. Calculating it inside Cimatron, no. That's based on what you've experienced in the past. But as you saw in Moldex 3D, once I run an analysis like that, I have very hard facts about water temperature, in, out. It understands everything. It understands the material the cavities are made out of, whether they're P20 or aluminum or whatever. So it can take so many factors into account and really give you accurate numbers.
Someone is asking, can you explain the pressure spike in the filling graph?
Well, there was two. The first one is in the gate, which is a very small opening, and so the pressure does spike there. The other one in the graph was at the very end of fill, and again, I'm not the best expert on the Moldex 3D product, but I'm pretty impressed with it. So I believe that is just something that happened at the last moment of fill.
All right, we did get a bunch come in here. Let me see. Can Moldex 3D do full flow simulation for die casting?
Well, yes and no. The material database is for plastic, and I believe that folks from Moldex 3D would tell you that that's what it's designed to do. Die casting, of course, is molding metal, and metal has some flow properties that are a little different than the way plastic would flow. I've heard of people using it because it's a simulation product, but that would be a question best asked of our friends at Moldex 3D.
We are getting a lot of questions about Moldex 3D. Somebody said, what is the difference between Moldex 3D and mold flow?
No more than the difference between Cimatron and another CAD system. They're similar products. They're competitors. Moldex 3D is used all over the world, and in my opinion, is really an impressive product.
Can Cimatron do conformal cooling channel design?
Well, yes. I mean, it's a CAD system. The point I was hoping to make about the conformal is that the whole point, the whole idea is to do something that's similar to the shape of the part. I had that one there that I designed up. It was done with a spiral, not tough to do. It was done with some offset of surfaces, not tough to do. The other thing that people are going to use when it comes to conformal cooling is they're going to use STL models, because a lot of these parts are repairs that are being done, or maybe something that's been scanned. And of course the STL model is very useful because it goes right into your rapid prototyping machine, into your 3D printer. Cimatron is actually working and has developed some other nice tools for dealing with these types of models, because they're not solids. STL files are really point cloud data. We can do some things with them, machine them. In our next version this spring, we're actually doing cuts on them, and a lot of the things that you would think would be only a solid on STL. So again, conformal cooling, it's going to be different for every shape, but yes, Cimatron's very capable of helping design those types of channels.
Right. Let's see. Can you import a tool design from another CAD package and use the cooling analysis to prove out the design?
That's a good question, because the thing that I do before you run the analysis, you have to identify those ins and outs and plugs. So the answer is yes, but it's a conditional yes. I think you'd have to spend a minute in Cimatron and add in those types of plugs at the end of the lines. If the imported design already had them, it's possible we could tag them with attributes, you know, so that, oh, this is a plug, this is a connector. I haven't tried it. But once we had the attributes in place, sure, then you could run the circuit.
Right. Will Cimatron calculate the flow rate needed to achieve turbulent flow?
No, I'm afraid Cimatron is really just the design end of the product. Turbulent flow is the only number I know of that indicates it is that Reynolds number. At a certain value of Reynolds number, you've generally got turbulent water flow. So again, a lot of what we design in Cimatron is based on experience, and now we have something like Moldex 3D to back up that experience and give us the numbers that would show. Anything besides a straight through line is going to be turbulent water flow generally. If you put a baffle in the way, if you turn a corner, you're going to get some mixing. But it's important to have good mixing, and the analysis software can show that.
All right. I think we've answered all the questions so far. At this point, Dan, I want to thank you for your presentation and for answering all the questions. For those who attended and who would like more information or have further questions, you can contact Cimatron directly.